diameter is 8 millimeter. Okay, and 12 millimeter diameter pins are used at point D and point B. So this is point B and point D. So here, point B and point D here, the diameter is 12 millimeter. Okay, 12 millimeter. Okay, knowing that the ultimate shear stress is 100 megapascal in all connection. Okay, so for the pin, okay, for the pin, we have a tau is equal to this is tau ultimate. This is tau ultimate equal to 100 megapascal. Okay, and the ultimate normal stress, average normal stress, mean that here is the sigma. Okay, equal to 250 megapascal in each of the two links. So these are two links. These are two links. Okay, this is a link, and the sigma equal to 250 megapascal. Okay, in each of the two link. 250 megapascal for each link. So we have two here. So we have one, we have two here. We have two links. Okay, it's attached together. Okay, two links join B and D. So determine the allowable load P. So this is the P if the overall Fs equal to 3. So this 3 equal to Fs. Fs factor of safety. So we want to determine what is the P. What is the maximum P we can apply at point C if we consider the shear stress at the pin A, pin B, and pin D, the maximum equal to 100 megapascal. And then for the link, if for the each link is 250 megapascal, and Fs in this case equal to 3. So we have considered this 3. Okay, pin, this one first, this one second, and this is the third one. So we have considered all these three requirements to fulfill for the system, and then what is the maximum P, okay, can be applied at point C. Okay, so this is the question. Normally this question is for the final exam. So you should analyze. You should analyze. Okay. Okay. Before I proceed, let me allow your friend to join first. Okay. 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 Can you understand this problem? Okay. You understand this problem first before we proceed? Okay. So I hope you can understand. Okay, that is all requirement. We have the tau ultimate. We have sigma ultimate. So this one is sigma ultimate or sigma maximum. So sigma maximum or sigma field. So the same thing. And then we have Fs equal to 3. So in this case, you have to apply the Fs for tau and Fs for sigma. And then after that, you can compare the question, and then you choose what is the maximum load P can be applied at C. So as usual, we have to start in this to solve this problem. Okay, by the first step is to draw free body diagram. Draw free body diagram. So we have two members here. Okay, members A, B, C, and BD, and BD. So which member we should consider to draw the free body diagram? Is it A, B, C, or BD, please? Which member? Which body?
ABC.
A, B, C, should be A, B, C, A, B, C. So this is the free body diagram. So this is FBD. It's very simple, FBD. FBD. Okay, so if you can see that BD this is a link. So link means that this is a two force member. So that's why we have only one force here, FBD. Okay, and then there's a P. We want to determine what is the P here. And then we have FA. FA. So actually at point A, we have two forces. So this is, let's say, is EX. And then from the total Fx equals to 0, total Fx equals to 0. So there is no force in X direction except Ax. So that's why in this case, Ax equals to 0. Okay, so we have this one, A Fa or Ay, A force Y, force at A in Y direction. So we have only two unknown here, Fa and Fpt. Yeah? So and Fp is we want to determine. So it means that we have three unknown. We have three unknown. So in this case, we can apply the total moment about maybe about E or about C or about B equal to 0, and then we can apply the total Fy, and then we have to create another equation because we have three unknown here, so we must at least three equation. Okay, so let me allow your friend to join. No. Okay, sorry. Okay, so this is free body diagram, and then from this free body diagram, we try to analyze the force. Okay, so in this case, you can see that okay, we have three unknown FA, FBD, and a P. So our task now is to write the equation. And what is the relationship between P and FBD, and relationship between P and FA, P and FA. Okay, so we can start with the first one is moment. Okay, moment about B or moment about A. So moment, let's say this is moment about B equal to 0. So we have 0.2 FA minus 0.18 P equal to 0. And then this is first relationship between P and FA. So this is the first one. And the second one is if we choose a moment about A equal to 0, so we have the relationship between P and FBD. So this is the second equation. Second equation. So a relationship between P and FA and P and FBD. So from that, so we can apply the Fs. Okay, so this is the area. This is area for the link BD. So link BD, this one. BD, if you cut it here, okay, the cross section is this one is 8. This one is 8, and this one is okay. Sorry. This one is it's not 8, and this is 20, and this one is 8. This one is 8. Okay, so the area equal to 0.02 multiplied by 0.08 equal to this one. This is the cross-sectional area for the link. For the link, and then this one is actually the relationship for the Fs. So we have Fs equal to tau ultimate, tau ultimate divided by tau allow, okay. Okay, so Fs equal to 3, this one equal to 3. Okay, so tau ultimate equal to tau ultimate. Okay, okay, so this is for the pin. So this is the pin, and then for the link BD, the same thing. The same thing. Fs for the link equal to sigma ultimate divided by the sigma allowable. Okay, allowable. So this is for the link. This is for the link. Okay, this is for a pin. This is for a pin. Okay, this one is for a pin. So pin means that pin A, pin B, and pin D. And the link here is link BD. Okay. Okay, this is a formula that we have. So now we go one by one. For example, for the link BD. Okay, for the link BD. So this relationship between the sigma ultimate and sigma allow. So Fs equal to 3. So you can rearrange. We can rearrange the position of this symbol. So we want to determine the F. F, for example, this one is F allow. Fs equal to. So we have sigma ultimate and sigma ultimate. Okay, divide by sigma allow equal to F divide by A. F divide by A. F divide by the area. Sorry, F divide by the area. So and then you want to, if you want to determine the F, okay, you can rearrange the expression. So now become the F. Okay, so this is Fs. So A, you can go to the upwards. So this is A, and this is my ultimate. So this is 2. These two because we have two parts. So we have this one first, and this one is second. We have two link, left and right. Okay, so that's why we have 2 here. Okay, we have 2. So 2 and sigma ultimate equal to 50. Okay, and then the area equal to this one, and Fs equal to this one. So FBD, this F, this SBD equal to 26.7 kilonewton here. And the relationship between P and FBD equals this one. So P equal to 10 over 19 FBD. So this one is FBD. Okay, so P in this case, if we consider the link, the maximum P equal to 14 kilonewton. P that can be applied here equal to, okay, equal to 14, equal to 14. Okay, based on the link, okay, the maximum P is equal to 14.04 kilonewton. Okay, so this is based on the Fs and sigma ultimate. Okay, sigma ultimate. So now we go to the second part. Is about the when we consider for the pin. Okay, when we consider the pin. So pin we have at A and at B and at D. So actually at A is the same. A is tau equal to V over A, V over A. And at point A, at pin A, this is a single or double shear at A. Pin A. Pin A is single or double?
Double.
Yes, double. So the double, you have to divide by 2. Okay, what about the at point B? At B and point D. B and D is a double or single shear?
Double.
You can see here. You can see here.
Double.
Okay, this is double, also double. So this is for A, and for the B, tau B. So tau B, okay, the same thing, equal to V divided by 2 because of double shear divided by the area. Okay, so this is formula for the tau. And then tau B is equal to tau D because F at B equal to F at D. Okay, because this is two force member. Okay, so now we go to the second part. Okay, when we consider pin A, okay, pin A, pin B, and pin D. So this is double shear. So for the pin A, this is the area for the pin A. Okay, pi. So this is from the pi. This is D. Pi D squared divided by 4. Okay, this is the area for the pin, and the same thing. This is the F. Okay, we consider the Fs. Fs, if you still remember, Fs equal to tau ultimate. Tau ultimate divided by tau allowable. So tau ultimate. So tau allowable in this case equal to, okay, V over 2 divided by the area. Okay, so this is tau allow. So this is tau allow. And then if you can rearrange this one, so V here refer to the force at pin A. So you can put the V at A or P or FA. FA is the same. So this as FA is the same as V here. Okay, so you can rearrange this formula. So become FA equal to 2 tau ultimate, okay, total ultimate area divided by Fs. Fs. Okay, so you just put it all the information. Okay, 2 because of this one. Okay, 100. This is tau ultimate, and the area equal to 50.266 10 minus 6, and 3 here equal to Fs. This is Fs. Okay, based on this, you can calculate the Fa of V here equal to 3.35251 kilonewton, and this is the relationship between P and Fa. So from here, you can calculate the P, the maximum P that you can apply at point C equal to 3.72 kilonewton. So now you have two P. The first P is based on the, if you consider the sigma, Kp equal to, how much last one? 14, 14, equal to 14. This one is 14 kilonewton. If you consider the tau ultimate, so P equal to 3.72 kilonewton. So now, what is the maximum P that can be applied at point C? Is it 14 or 3.72? Hello? What is the maximum P? Let me allow your friends to join first.
Ooh.
So what is maximum P?
Well,
14, sir.
Okay? Can I repeat? Based on our calculation, if we consider the sigma, okay, for the link, P, maximum P that can be applied at point C equal to 14 kilonewton. And then if we consider the pin is, here it refer to the ultimate shear stress, okay, for the pin P, for the pin A equal to P 3.72. Okay, so in this case, but we have another one. We have another one for the pin B and D. Okay, so based on pin B and pin D, okay, so this is the relationship between the between P and FPD. So the maximum P equal to 3.97. So this is based on the tau at pin A. So tau at pin B and D. So P equal to 3.97 kilonewton. So we have three answers here. So P, one, second one, and third one. So which one is the answer?
3.72.
Huh?
3.72.
3.72, the maximum, the maximum. Okay, so the maximum, yes, the answer is 3.72. This is the maximum P that can be applied at point C, okay, to make sure, okay, to make sure the link BD, okay, pin A and pin B and pin D are safe. Okay, if you choose 3.97, okay, so only pin B and the link BD is safe. But if you choose this one, okay, 3.72 all means that the link BD, pin A, pin B, and pin D are safe. So that's why in this case the answer is 3.72. Okay, 3.72. Okay, 3.72. Okay, so this is the answer. Okay, so you can see that from this one, you have to analyze. You have to analyze this problem, and then based on that, you can give the answer based on the requirement. Based on the requirement that as mentioned in this question. Okay, I think so. That's all for the chapter 1. If you have any problem, you have any question so far, you can understand. So we finish one chapter. Any question before we proceed to chapter 2 about strain? About strain. Any question, please? Any question?
No question.
No.
No question, doctor.
So and then we have example 17. I think this one is quite similar to example 16. So I hope you can go through and then study about that. So we have an answer here. Okay, and then example 18, same one. Okay, so it involve Fs involve sigma field. Okay, intention, and then the tau field for each one. So in this case, you have to consider one by one, and then based on that, you can choose the answer. Okay, you have to decide based on the P. I think this one is we have a 3 different P, and then based on that, you choose the smallest one to make sure the site is safer. Okay. Okay, I think that is for chapter 1. So now we go to chapter 2. So chapter 2 about the strain. The strain. Okay. So so what is the difference between chapter 1 and chapter 2? So in chapter 1, okay, we study about the average normal stress. Okay, and average shear stress. Okay, average shear stress. So let's say we have the body like this. Okay, and then when we apply the force P here, okay, so in this case, what happened is the stress will develop in this body. Okay, the stress will develop. So how to measure the stress? Okay, stress here refers to average normal stress. This is sigma. Sigma equal to P over A. P over A. P is the normal force. A is the cross-sectional area. Okay, so P may be in tensile like this, or P may be in compression like this, P. So this is this sigma is positive, and here is sigma equal to negative. Okay, because this is in compression. Okay, compression. Okay, so that is in chapter 1. And then what happened in chapter 2 about the strain? Strain is we want to measure the deformation of this body. So let's say if we apply the force P here, and this P will increase. Okay, the magnitude of P will increase. Okay, so what happened to this body? So this body will deform. Deform means that the body will change their size or their shape. Okay, So why? Because this body is not rigid anymore. It's not rigid. So that's why it deforms. At certain stage, when we increase the force P, so the body will change, will deform. Okay, if we apply the force P in this case to this direction, what happens is if this one is equal to L, the length, okay, the length. So when we apply the P, so the length is increased, and the diameter, if the cross section is like this is cross section, and the diameter will decrease. Okay, so the same thing. So the same thing. If we push again the body, so this is L, the length. So what happened is the length is decreased and the cross section is increased. So this is the deformation. So how to measure this deformation is based on this strain. Okay, this is the overview for this chapter. Okay. Okay, so we go to the first one. Okay, deformation. Okay, when a force is applied to a body, so it will change the body shape and size. Okay, maybe the size becomes smaller or become larger. Okay, the shape maybe from the circular now become maybe oval. Okay, let's say for example, or maybe from the square become rectangular. So this is the shape, the change in the shape. So the changes are, these changes are deformation. Okay, for example, this one. Okay, so this is before deformation. Okay, before deformation, and we pull. So this one is pull upward. Okay, P. So what happened? You can see that the change of their shape and size. Okay, so I think you can visualize. Okay, you can visualize or you can imagine what happened to this body when we pull or when we push. Okay, pull means that in tension, and when we push in compression. Okay, so if we pull, the changes in their size or their length we call as elongation, okay, or expansion, or when we push, okay, we call as in contraction, because the length, okay, becomes smaller, so we call as contraction. Okay, so this is the term that we have used in this chapter. Okay, so how to measure? So based on the formula, we have the strain, we call as strain. So for the strain, we have also two part. First is we call as the normal strain, and the second part is we call as the shear strain. Okay, normal strain and shear strain. As stress, we have normal stress and shear stress. So for the strain, we have normal strain and shear strain. So what is normal strain? The elongation or contraction, So this one is referred to the elongation is in tension. This one is compression, in compression. Tension and compression. When we apply the force, okay, in tension, so the body become expansion or elongation. When it compress, become contraction. So the elongation or contraction of the line segment per unit length is referred as a normal strain, or the symbol equal to, we call as epsilon, So this one is epsilon. Epsilon equal to delta S dash minus delta S divided by delta S. Okay, so because S is referred to the length, okay, so normally we the unit is millimeter or meter. Okay, and also this one is equal to millimeter or meter. It doesn't matter. So the unit, what is the unit? Unit is we call as dimensionless. Dimensionless because we can cancel this one. But in practice, we maintain. Let's say what is the value of epsilon? Epsilon equal to, let's say, the 10 minus 3 we maintain this one, millimeter over millimeter. So just to give the idea, what is 10 minus 3? Is it meter or millimeter? So if we have a unit millimeter or meter, we can imagine the size and so on. So that's why we maintain. But in for the mathematics, we can cancel because for the top part and the bottom part is the same. We can cancel. Okay, but in this our case, engineering, we maintain that unit. That unit. Okay. So to give the diagram to help you to understand this one. Okay, let's say this is the body. So this is the body. Okay, so this is point A and point B, and the distance between point A and point B equal to delta S. This is we call as the original length. This is the original length. Original length. Okay, this is the original length. The original length means that the length of the body, the distance of the body of the point when the body is free from the force. Okay, so we call as undeformed or before deformation. So this is the deformation. After deform, we can see that the distance from point A to point B now is changed. Okay, let's say this point A now become A dash and B is B dash, and delta S or the distance from A to B, the original length equal to delta S, so now become delta S dash. Okay, so from here we can put in our formula. Okay, as before, say this one. Okay, so we can determine the average normal strain or epsilon. Epsilon. Okay, so this is just to give you the view about what happened to this body. Let's say this is the body AC before deformation, and A is the cross-sectional area. Okay, so when we apply the force P, what happened is the body BC now become longer. Okay, expand. So this is we call as the delta. Okay, this is delta. So delta here equal to delta. So delta here equal to the final length. Final length is let's say this is a BC dash. BC dash. Okay, minus BC, the original length. Okay, this is the final length. This is the original length, and divide by the original length. Okay, original length equal to BC. Okay, BC. So this is the delta. Okay, sorry. So this is delta. This is delta. This one. Okay. So when we want to go between the epsilon, so delta divided by L. So the epsilon equal to delta divided by L. L is the original length. Okay, L is the original length. So this one equal to BC dash minus BC divided by BC. Okay, that is the epsilon or average normal strain. Okay, the same thing if we have the double cross-sectional area, this one. So the epsilon is the same, equal to delta divided by L. And if we have the double length, 2L instead of L, so the formula is the same. Okay, epsilon equal to delta divided by 2L. So the epsilon equal to delta divided by L. So in this case, what you have to understand is for the normal strain, or the symbol is the epsilon, okay, equal to delta divided by L. Okay, how to determine delta? Delta is the final length. Okay, final length means that the length after deformation, okay, minus the original length. Okay, or the length of the body before deformation. So this is the delta. So from that we can determine the normal strain. Okay, and then the second part is shear strain. Okay, shear strain. A shear strain means that in this case we want to measure. We want to measure the deformation of the body based on the angle. Okay, we measure the strain of the body based on the angle. Based on the angle. Okay, so for example, this one, this is the body. Okay, the angle between AC and AB equal to half pi. Half pi means that this one is 90 degree, 90 degree. So this is before deformation. And after the deformation, we can see that the line of AC and AB now change. So the angle theta dash, the theta dash, maybe the theta dash is less than 90 degree or maybe more than 90 degree. Okay, so we compare before and after. Okay, we compare before and after. Maybe if the angle is less than 90 degree, okay, so we have the positive shear strain, and if this theta dash is more than 90 degree, so we have the negative shear strain. Okay, so negative shear strain. So this is another part of the strain. We call it shear strain. How we can measure the deformation of the body, okay, based on the angle. Okay, the deformation of the body based on the angle. We can measure. We can compare the angle. What happened to the angle? Okay, before and after. So from here, we can measure that we call as the shear strain. Okay, so we go to the first example in this case. Okay, this is about the average normal strain. So epsilon. Okay, so a force acting on the grips. So this is the grips. This is the grips. Okay, of the lever arm shown in the figure A. Cause the arm is to rotate clockwise through an angle of theta is 0.02 radian. So this angle is 0.002 radian. Okay, as shown in figure B. Okay, determine the average normal strain. So average normal strain. So this is epsilon. Okay, developed in the wire BC. Okay, so from this diagram, we know that 1 millimeter here is the length of the wire BC before deformation. So this is LBC. This is LBC. This is the original length. 1 meter is the original length. So after we pull this one, we pull to this direction. So what happened is this lever now rotate to the direction and the angle equal to 0.02 radian. So of course, the wire BC now become longer. Instead of the 1 meter here, so now CB dash now is more than 1 meter. So now we want to determine what is the final length here. Okay, what is the final length? So this is the final length. Okay, final length. Okay, final length or the length after deformation. Okay, the length after deformation. So how to determine this length? Okay, because you want to determine the delta. Okay, epsilon equal to delta divided by L. So delta equal to C B dash minus CB divided by the original length equal to CB or BC, CB. Okay, so CB here equal to 1 meter, CB here equal to 1 meter, so CB dash, what is the CB dash? What is the length of CB dash? Okay, the length of CB dash. And so this is, I think you know how to determine the length, okay, for CB dash, because the angle here is small, 0.02 radian. So you can apply the, let's say if we have the circle like this, we have a circle like this, you have a circle. We want to determine this, let's say this is point A, This is point B, this is point B. So this is the theta, this is the radius. What is the distance between point A and point B? So point A and point B, okay, SAB, SAB. Okay, how to determine the distance from A to B if the angle is small, 0.03 radian? What is the formula? What is the formula? The distance, this one. What is the formula? I think you know this one. The formula equal to how much? Formula is equal to, what is the formula?
R theta.
Huh? Equal to r theta. Yes, correct. Okay, so this formula is valid if the angle is small. If the angle is not small, so you cannot use this one. You cannot use this one. So based on this, you can determine the delta. This one, delta here, delta AB here, the distance from A to point B, actually equal to this one. So this distance, the distance. Okay, so since theta is small, so the stretch for your CB is BB dash equal to r theta. So r equal to 0.5 meter and theta is theta equal to 0.02 radians and r equal to 0.5 meter equal to 0.01 meter. So the average normal strain equal to this one as 0.01 divided by 1 meter. So this is the average normal strain, average normal strain. Okay, so the delta equal to 1.001 minus 1 divided, yes, this one. This is delta. Okay, 1.01 minus 1. So equal to 0.001. So the distance from B to B dash. Okay, so that is how we can solve this problem. Okay, based on the average normal strain. Average normal strain. Okay, so that is the example. Maybe this example we can solve it later. If we have another question about this one. Okay, so the next question is about the shear strain. About the shear strain. So this one. So this shear strain is based on the how we can measure the deformation of the body based on the angle. Okay, the changes in the angle. Okay, so I think we now is 11:48. So I think we take break. Take break 5 minutes. We take 5. Okay, is it you want to continue or take break?
You say
Take 5.
Okay, take 5. Take 5. So